Hey everyone, welcome to this video on optimization. My name is Sri and this video is a part of a course taught by Professor Roozbahani at Georgia Tech. In this video, we're going to walk through a sample optimization problem and hopefully give you a deeper understanding of how to handle similar problems in your homework. Before this video, please make sure that you've attended the lecture and that you've watched the recordings on Canvas. Alright, let's get started with the question. In this optimization question, we're asked to maximize this function which has variables x and y. Maximize f of x and y, which is given as 2x plus 3xy, subject to the following constraints. You have g1, which is x squared plus 4y squared less than or equal to 9, and you have g2 of x and y, which says that y has to be less than or equal to 1/2. And so this is how the question has been framed. You want to maximize f of xy subject to these constraints. Since these constraints are inequality constraints, in addition to defining and solving for the Lagrangian, we also need to satisfy the Karush-Kuhn-Tucker or the KKT conditions. The first step towards solving non-probabilistic optimization function is to define the Lagrange function. In probabilistic questions, we define the likelihood function before taking the derivative and setting that to 0. In this case, we first define the Lagrangian function. So let's do that. So part A, Lagrangian. So L of x and y. Now, if you remember from class, the Lagrangian is simply the function you want to optimize, and you want to subtract your constraints g1 and g2 after multiplying them with lambda. So you have something like f of x y minus lambda 1 times g1 minus lambda 2 times g2. And so that's your Lagrangian. We've written that out. Often these questions will ask you to minimize, that is to flip it from a maximization function to a minimization function, and then provide the Lagrange function for the minimization problem with the same constraints g1 and g2. So let's write that out as well. So let's make a quick note that this is the, or let me make a footnote. This is the maximization function, and if you're going to flip that to minimization, of course, when you're optimizing, maximization and minimization are basically the same thing. And so when we minimize, we flip the signs on the constraint functions. So the next step is to make sure that these functions are satisfying the KKT or the Karush-Kuhn-Tucker conditions. And so let's kind of state what they are and express them as mathematical equations to solve for. There are 4 Karush-Kuhn-Tucker conditions. You have the stationary condition, you have complementary slackness, primal feasibility, and dual feasibility. The first KKT condition we're going to start off with is the stationary condition. In this condition, we take the first order derivative of the Lagrangian function with respect to the variables in it, i.e. x and y. So we would need to calculate partial L with respect to partial x and partial Lagrangian with respect to y. When you take the partial derivative with respect to any specific variable, we treat any other variable we see as a constant. So let's solve for partial L, partial x, and so that would be kind of really quickly taking a look at this. Derivative of 2x would just be 2. Derivative of 3xy would be 3y. We can ignore 4y squared and 9 as your constants when you take the derivative with respect to x. So this will kind of resolve itself to 2 minus 2x lambda 1. And nothing over here has an x term in it, so this becomes 0. And so partial L partial x is nothing but 2 plus 3y minus 2x lambda 1, and we do set this to 0. This becomes our equation 1, partial L with partial y. Again, very similar story. We look at the we look at a Lagrangian function, and we find that 2x has no y terms, that gets cancelled out to 0. 3xy obviously resolves to 3x. Over here, lambda 1 x squared gets cancelled out, and minus 9 gets cancelled out, but 4y squared resolves itself to 8y minus 8y lambda 1, and minus lambda 2, and then minus half lambda 2 gets resolved to 0. So writing that out, we end up with 3x minus 8 lambda 1, or we're putting the lambdas last, so minus 8y lambda 1 minus lambda 2 equal to 0. That's our equation 2. So that's a stationary condition taken care of. Let's look at complementary slackness. Complementary slackness simply takes the constraints with the lambdas and sets it to 0. So let's look at what that would mean. So as I said, complementary slackness simply means taking lambda 1 times x squared plus 4y squared minus 9 equal to 0, and lambda 2 times y minus 1 half is equal to 0. And again, these are conditions that our values for x, y, lambda 1 and lambda 2 need to satisfy. The third KKT condition we look at is called primal feasibility. So primal feasibility simply takes your constraints and sets that to less than or equal to 0. So that would be, for us, x squared plus 4y squared minus 9 less than or equal to 0. And similarly, y minus 1 half is less than or equal to 0. And then the last one is dual feasibility, which simply states that your lambda 1 and lambda 2 are active, that is, they're both greater than or equal to 0. That lambda 1, comma lambda 2 are greater than or equal to 0. That's your equation 7. So now that we've defined these 4 KKT conditions as mathematical equations, 4 possibilities arise because you have 2 constraints. That is, case 1, constraint 1 is active, constraint 2 is active. Case 2, constraint 1 active, constraint 2 inactive. Case 3, constraint 1 inactive, constraint 2 active. And case 4, which is both constraints are inactive. As we work through these cases, the idea is we solve for values of x and y, and then values of lambda 1 and lambda 2 to find if these are valid candidate points for our defined Lagrangian function. So let's work through those. Since we have 2 constraints, there are 4 possibilities formed. We have 4. Let's look at case 1. In case 1, G1 is set to active. Oops, let's rewrite that. And G2 is set to active. And so what do we mean when these constraints are active? We simply mean that lambda 1 is greater than or equal to 0, and that lambda 2 is greater than or equal to 0. And as I said, the idea is to find values for x and y that could be valid options. And so I'm going to start off with the function for primal feasibility when we said y minus 1 half is less than or equal to 0. Now that we have a value for y, we can plug that into, say, into equation 5, where we have x squared plus 4y squared minus 9 equal to 0. We have a value for y, we can try to find a value for x. And so kind of plugging this, so use this in equation 5, you end up with x squared plus 4y squared minus 9 is equal to 0. If x squared plus 4 times 1/2 squared minus 9 is equal to 0, you have x squared plus 4 divided by 4 minus 9 equal to 0. If x squared minus 8 equal to 0, x squared is equal to 8. And of course, taking the square root on both sides, x can be plus or minus 2 root 2. And so at this point, we have two possible candidate points. We have 2 root 2 comma 1/2. Oops, sorry. So we have two possible candidate points. That would be 2 root 2 comma 0, not 0, 1/2 and minus 2 root 2 and 1/2. Now at this point, we don't know which of these points is valid. To determine that, we will plug these into an equation with lambda to determine if that value would, if that value for lambda 1 or lambda 2 satisfies our constraints defined up here, which is that g1, which is that lambda 1 and lambda 2 have to be greater than or equal to 0. So let's start plugging in these values into, let's see, which equation has lambda 1 and lambda 2 involved. Let's pick equation 1 over here. So let's start with the partial derivative of lambda with respect to x. So if I plug in, so let's kind of just write that out first. We have 2 plus 3y minus 2x times lambda 1 equal to 0. Okay, so simply rewriting the partial derivative of the Lagrangian with respect to x in terms of x and y, we find that lambda 1 is equal to 2 plus 3y divided by 2x. And so at this point, y is a constant positive value, whereas x can be positive or negative. If we let x be negative, that would result in a negative lambda 1, which violates dual feasibility. Therefore, x equals 2 root 2. And again, remember that at this point, all we have done is eliminate the possibility of minus 2 root 2 comma 1/2 being a valid candidate point, because you've shown that if we use those values, lambda 1 gives us an unacceptable value, which violates our KKT conditions. And so we still haven't proven that 2 root 2 comma 1/2 is a valid candidate point. So let's see if it is in fact valid. If you plug in x equals 2 root 2 and y equals 1/2, done some math off screen, lambda 1 is equal to 7 over 8 root 2. You can do the math and double check for yourself. This is, of course, greater than 0, and lambda 1 is valid. Since lambda 1 greater than or equal to 0 has been fulfilled, 2 root 2 comma 1/2 might be a possibility. And so let's use the second equation to verify that lambda 2 is also satisfied. Remember that equation 2 is nothing but the partial derivative of the Lagrangian with respect to y, which is 3x minus 8 lambda 1 y minus lambda 2 equal to 0. And again, remember that this equation is coming all the way from up here when we've done the math for the stationary condition. So just using that equation, set that to 0. We have a value for lambda 1, we have a potential value for x and a value for y, and so all we're doing is solving for lambda 2. So you take 3 times 2 root 2 minus 8 times 7 divided by 8 root 2 times 1/2, and set that equal to lambda 2. And again, you'll just have to trust me. I've done some math off screen. Lambda 2 is equal to 17 divided by 2 root 2, which is 6.0104. Since lambda 2 is also fulfilled, 2 root 2 comma 1/2 is a valid candidate point. So since lambda 1 and lambda 2 are greater than or equal to 0, 2 root 2 comma 1/2 let's look at case 2. In case 2, you have constraint G1 active and constraint G2 inactive. Now, last time when we talked about case 1, when we said both of these constraints are active, we said that they're both active, and so therefore lambda 1 and lambda 2 must be greater than or equal to 0. In this case, we're saying that G2 is inactive. That simply means that we're setting lambda 2 to be equal to 0 and lambda 1 to be greater than or equal to 0. And so why are we setting something to 0? If you consider the Lagrangian function, if we set any given constraint, if we set the lambda to 0, then that means that this constraint no longer applies, and so your function kind of devolves into the function to optimize and any other remaining constraints. So if we say that lambda 2 is not active, your function becomes 2x plus 3xy minus lambda 1 times x squared plus 4y squared minus 9. So going back to, okay, in case 2, again, I'm going to start off with y minus half is less than 0. Y minus half is less than 0. And I'm also going to start off with the other constraint, which is that x squared plus 4y squared minus 9 is equal to 0. And again, rewriting this, I'm going to achieve x squared is equal to 9 minus 4y squared. That means x is the square root, plus and minus, of course, 9 minus 4y squared. Awesome. I'm gonna use the partial derivative of lambda with respect to y to get 3x minus 8 lambda 1 y minus lambda 2 is equal to 0. We know that lambda 2 is 0 because we just said that constraint 2 is inactive, so that's equal to 0. I'm going to express lambda 1 in terms of x and y. So you have 3x is equal to 8y lambda 1, which means lambda 1 is equal to 3x divided by 8y. And similarly, I'm also going to use the other equation, which is the other partial derivative of L with respect to x, which is nothing but 2 plus 3y minus 2x lambda 1 equal to 0. If you remember that, if you kind of solve again for lambda 1, you end up with lambda 1 is equal to 2 plus 3y divided by 2x. And so we have two different expressions for lambda 1, and if we set them equal to each other, we can solve for values of x and y. So setting lambda 1 and that lambda 1, you have 3x divided by 8y equals 2 plus 3y divided by 2x. Cross multiplying, you end up with 2 times 3, 6, x squared plus 16y, sorry, not plus, equals 16y plus 24y squared. Again, I'm going to divide by 6 over here. So let's see, you have x squared is equal to 16 by 6. We can express that as 8 by 3y plus 4y squared. And so we have this equation for x, which we can plug in to this equation for x that we defined earlier here, which is x squared equals 9 minus 4y squared. So kind of, let's do that. So plugging the value of x squared into x squared plus 4y squared minus 9 equal to 0. We end up with 4y squared plus 8 third y plus 4y squared minus 9 equal to 0. And again, at this point, we have an equation in terms of y, so let's solve for values of y, which would be 8y squared plus 8 thirds y minus 9 equal to 0. I'm going to divide by 8 to end up with y squared plus 1/3 y minus 9 over 8 equal to 0. At this point, I'm going to use the quadratic formula to solve for values of y. So y is equal to minus b, so minus 1/3 plus or minus the determinant, which is b squared minus 4ac, so 1 over 3 whole squared minus 4 times a, which is 1, times c, which is minus 9 over 8, divided by 2a, which is 2 times 1. So you have, simplifying this a bit further, minus 1/3 plus or minus the square root of 1 over 9 minus or plus 36 divided by 8 divided by 2. That gives us two possible options. You have minus 2 plus the square root of 166 divided by 12, or if minus 2 minus the square root of 166 divided by 12. When we consider the case of the plus case, this ends up being more than 1/2, which violates the constraint that y has to be less than 1/2, which is your constraint G1 all the way up here. So, sorry, G2. So we can kind of ignore this constraint, ignore this case, and we set y equals minus 2 minus square root of 166 divided by 12, which is equal to minus 1.2403, which satisfies constraint G2. Substituting this into x, we said earlier that x is equal to the square root of 9 minus 4y squared. Plugging this in, we end up with x is equal to plus or minus 1.687. And since we've chosen y equals minus 1.2403, and we've defined lambda 1 up here as 3x divided by 8y, we need to choose a negative value for y, otherwise lambda 1 would be, so that the negative signs can cancel out, otherwise lambda 1 would be less than 0, which would violate the dual feasibility constraint again, and so that will make us choose the positive case. It's kind of formalizing that. From lambda 1 equals 3x divided by 8y, we must choose negative value of x to satisfy the lambda 1 greater than or equal to 0 constraint, since the negative value of y has been chosen. Again, as we go through this question, we're kind of solving these cases. The thing I want you to take away from this is that the goal is to keep finding values of x, y, and lambda 1 and lambda 2 such that they all satisfy their constraints and the KKT conditions. And so in the first case, if you remember, we first solved for values of x and y, and then when we have multiple options, we then plug different values into equations with lambda 1 and lambda 2 to kind of find out which ones gave us valid candidate points. Similarly, in this case, in the second case, when we started off with finding values of x and y, and then setting them equal to plugging them into equations with lambda 1. The work we did over here with lambda 1, finding out these two equations, can honestly be done at the very end as well, because all this work does is to help you identify which candidate points are valid and not. And so from this case, we find out that we do have a valid candidate point. So we find you have minus 1 point. So what was that again? Minus 1.68707, and then what? Minus 1.2403 is a valid candidate. Now, of course, we found a candidate point in each of these first two cases. It's important to remember that we may find one candidate point, we may find more than one, we may find no valid candidate points. Let's look at case 3. Case 3. And so if you remember, in case 1 we had both constraints active. In case 2 you have case 1 active, case 2 inactive. In case 3 you have constraint G1 inactive and G2 active. And if you remember again, when we said that a constraint is inactive, we simply said that the lambda for that constraint equal to 0. And so in this case, lambda 1 is equal to 0, but lambda 2 is greater than or equal to 0. Again, sorry, just giving us a bit of space. Let's start with the equation y minus 1/2 is greater than or equal to 0. That gives us y is equal to 1/2. Okay, that's great. This time we can use the stationary condition partial derivative with respect to x. So let's say 2 plus 3y minus 2x lambda 1 equal to 0. And now, of course, you might be wondering throughout this question, why am I choosing specific equations? And the simple answer is that I'm trying to find equations that will help me achieve my goal of finding values of x, y, lambda 1 and lambda 2 that help me solve this question. In this example, I know that I found a value for y, I know that lambda 1 is 0, so this term gets cancelled out, and I have 2 plus 3 times 1/2 is equal to 0. Now obviously this equation doesn't make any sense, this is not possible, and so this is false, so no solutions from this case are valid, which means that we found no valid candidate points from this case. So since this is false, no valid candidate points have been found. So yeah, that's case 3. Let's move on to case 4, which is the case that both constraints are inactive. So G1 inactive, G2 inactive, which means lambda 1 is 0, but lambda 2 is also 0. So let's start with, again, I'm trying to think of an equation from the KKT conditions that you've established all the way in the beginning. I'm trying to think of something that's going to help me either find candidate points or disprove that there aren't any valid candidate points. And so I'm thinking of using this equation right here, which is the derivative of the Lagrangian with respect to y. If I set lambda 1 and lambda 2 to be 0, since both constraints are inactive, 3x equals 0, x is 0, that means I found a value for x pretty quickly and easily, so let's go with that. So kind of scrolling back down. So using 3x minus 8y lambda 1 minus lambda 2 equal to 0. As you established, both constraints are inactive, so lambda 1 and lambda 2 are 0. And so these both cancel out, or not cancel out, they're both equal to 0. 3x equal to 0, which means x is equal to 0. And so plugging this into the partial derivative of x, which is 2 plus 3y minus 2x lambda 1 equals 0. Again, as we've said, lambda 1 is 0, x is 0, so this term is 0. 2 plus 3y equal to 0, which says y is equal to minus 2 over 3. And so we found a possible candidate point, 0, comma minus 2 over 3. Since y is less than 1/2, it's a valid candidate point. And since lambda 1 and lambda 2 are equal to 0, they also satisfy the condition of dual feasibility. And so therefore, we found a new valid candidate point. Therefore, 0, comma minus 2 over 3 is a valid candidate point. And so kind of listing it out again. that's what part D, I think. Let's see. These 4 cases were part C, right? So listing our valid candidate points. The first one we found was point 2 root 2 comma 1/2 with lambda 1 and lambda 2 equal to 7 over 8 root 2 and 17 over 2 root 2. The second valid candidate point was minus 1.687 and minus 1.240 with lambda 1 and lambda 2 being equal to 0.51 and 0. And the last candidate point that you just found is 0 comma minus 2 over 3 with lambda 1 and lambda 2 both being equal to 0. So we have 3 valid candidate points. The last part of this question is doing the convexity check. And of course, to do that, we want to find the value at which f is the largest. And so we do that by simply evaluating the function f at each of our valid candidate points. And so these, of course, as we just said, are your candidate points. And you want to evaluate not the Lagrangian, not the not any of the stuff that we've done, just the function itself at those candidate points. And so if you do that, what you find is that the value of f, again, kind of trust me on this, but if you do the math, you'll find that the function of f evaluated at 2 root 2 comma 1/2 is something roughly equivalent to 9.899. Function f evaluated at minus 1.68 comma minus 1.24 is roughly equivalent to 2.9, and the function f evaluated at 0 comma minus 2 over 3 is roughly equivalent to 0. Since the function at 2 root 2 comma 1/2 has the highest value, we want to check its concavity. First, for the concavity check, again, we do use the Lagrangian, we don't use f of x. So if you remember, the Lagrangian is 2x plus 3xy minus lambda 1 times x squared plus 4y squared minus 9 minus lambda 2 times y minus 1/2. At this point, of course, we do want to set, we have the candidate points 2 root 2 comma 1/2 are only found at lambda 1 and lambda 2 being equal to these values. So if we plug those in, we end up with a Lagrangian that looks something like this. 2x plus 3xy minus 7 over 8 root 2 x squared minus 7 over 2 root 2 y squared minus 17 over 2 root 2 times y plus 97 divided by 8 root 2. Of course, this looks a bit scary, a lot of big numbers, lots of radicals, but all I've really done is substituted the value of lambda 1 and lambda 2 that we found earlier and simplified. So if you do that, you'll find that the Lagrangian can be expressed this way. The concavity check for any function is taking the second order derivative and checking if it's greater than or less than 0. Since this is a function with more than one variable, we need to calculate the Hessian matrix. If you remember again from class, the Hessian matrix is nothing but the second order derivative of the Lagrangian with respect to x, the second order derivative of the Lagrangian with respect to x, and then with y, the second order derivative of the Lagrangian with respect to x, with y, and then with x, and finally the partial derivative with respect to y. So let's solve for these values. Partial derivative of the Lagrangian with respect to x is 2x plus 3y minus 7 divided by 4 root 2 of x, partial L, partial, the second order derivative would be 2 minus 7 divided by 4 root 2, which is roughly equal to minus 1.237. Partial L with respect to partial x, then partial y. So just taking the derivative of this over here with respect to y, we end up with 3. Again, continuing the same trend, partial L, partial y is equal to 3x minus 7 over root 2 y minus 17 divided by 2 root 2. The second order derivative with respect to y is just minus 7 over root 2, which again kind of simplifies to minus 4.950. Derivative with respect to y and then with x, which is just taking the derivative of this right here with respect to x, is 3. And so at this point we have everything we want to fill out our Hessian matrix, and the concavity check is simply its determinant, which is why we have the symbols for the determinant, of course. So let's go ahead and do that. And so to take the determinant, of course, you just cross multiply minus 1.237 times minus 4.950 minus 3 times 3. So you have something like this simplifies to minus 2.87. And since the determinant of the Hessian matrix is less than 0, we have a saddle point. And that is how we solve questions like this. I hope this helped you gain a better understanding of how to approach non-probabilistic optimization functions. Please do reach out to us in office hours if you need any more help. You can also post on EdSTEM to get immediate support.